Hello Internet, my name is Quinn and this is Blondihacks. I'm going to start a new tool build this week. I'm going to be building a tool sharpening system, specifically in fact the Eccentric Engineering tool and cutter sharpening system. This is not a sponsored video, but Gary did send me this kit for free, just kind of as a thank you for showing his tools on my channel over the years, but I am going to give you my honest impressions of this kit as we build it. This will do drills, end mills, broaches, all kinds of stuff, and it attaches to any standard 6 or 8 inch bench grinder. I think this is a really great middle ground for hobbyists, kind of between a full tool and cutter grinder system and trying to freehand sharpen drills and such on your bench grinder. Let's give this thing a try right now. Let's take a look at the pieces in this kit. On top, of course, are the drawings. There's a whole book of them, in fact. You know you're in for it when the drawings for a project come in a book. Now, you can order this just as the drawings shown here, or you can order a fully assembled tool sharpening system, or you can do what I've got here, which is kind of in the middle. It's got the drawings and it's got bar stock for many of the parts, and some of the parts are actually fully finished. Other pieces like these brackets are partially finished, so it's a little bit of a mix. It's kind of a good balance actually, because some of these pieces, they've done the steps for you that would be difficult to do in a home shop accurately, and then you just get to do the fun parts. Some pieces are also fully finished via the laser and just need a little bit of cleanup before use. Now, one thing missing in my box was the table. There's supposed to be a laser cut piece of steel for that, but Gary had packed this kit in loosely around some other stuff he was sending me, and I guess the table didn't quite make it into the box, but that's okay. One thing I have around here is steel, so I'm sure I have something that will do. The drawings specify 4mm thickness. I've got some 3/16 here, which will be close enough. Unfortunately, this piece does have a slight banana to it, so I'm going to have to try and find a flat section of it. Luckily, we only need 150mm square, so I'm going to see if I can find a section of this piece that large that is flat. And in fact, this corner over here looks pretty good, so I'll cut the table out of this. Over to the bandsaw to rough cut this thing to approximate dimension. These portable bandsaws, as you've seen me use a lot on my channel, are really awesome for the home gamer. The main downside to them is the limited throat. On one side of the blade, they actually have infinite depth because the right-hand side of the blade is clear of the body of the saw. However, on the left, they are limited to a 6-inch throat. What that means is that there's a bit of an art to getting the most out of these saws. If you do just the right amount of planning ahead and cutting away scrap pieces into smaller pieces and occasionally flipping the piece over, you can arrange it so that the long cuts that you need to make are always on the right-hand side of the saw blade, where that twist in the blade gives you infinite throat depth past the body of the saw. Sometimes it means you have to chop up your offcuts into smaller pieces, which is, a little bit more wasteful, but you can get it done. Now, all the drawings for this project are in metric. So, buckle up friends, we're going metric. Yay! Wait, hold on. Just waiting for America and Myanmar to finish. Good. Oh, wait, there's a couple of Canadians in there. Officially, Canada is a metric country, but the reality on the ground is, it's complicated. To finish the edges of that plate, I'm going to use a setup that I like very much. I start by reversing the movable jaw on my vise. This gives me a lot of extra width for holding thin stock. It's a pretty standard feature of most milling vices. You can also do this with the fixed jaw, but I have never actually done that because if you put the fixed jaw on the back, you get like another inch, but then you've moved the fixed jaw, which means you have to re-indicate in the vise. And if you have to do that anyway, you might as well take the vise off and work directly on the table. Next, I set an adjustable parallel to the exact same height as the top deck of the vise. Then that parallel lives up against the fixed jaw, and that gives me an even surface onto which I can set my fixture plate. Now, this fixture plate is a 6x12 aluminum fixture plate made by Dayton CNC Products, #not sponsored, but people ask me about it a lot. And you can, of course, bolt it directly to your mill table, but I've also found I can put it in the vise like this, which is a much quicker setup, and I get a lot more use out of this fixture plate by doing this. One caveat with this fixture plate, on the one that I got, I found that the edges were not machined perfectly parallel to the fixture pin holes on the inside of the plate. So if you hold it in a vise like this, your fixture pin holes are not necessarily going to be parallel to your vise jaw. So I actually remachined the outside edge of this fixture plate to fix that issue. Something to keep in mind when buying fixtures like this or fixture plates. Don't assume that just because a surface on your fixture is flat and looks straight and parallel to other things that it is. If the designer of that fixture didn't intend you to use it that way, they may not have cared very much if those edges were correctly machined relative to each other. So always check. After cleaning up one edge, I've now got a reference from which to use to start squaring up the entire plate. It's important to deburr that cut before proceeding because that cut is going to be our reference, and we want to make sure that the plate sits nicely down on the fixture plate for subsequent cuts. So that should be smooth to the touch before proceeding. Now I'm going to make the second edge parallel to the first, so I'm going to set it up like this, and the edge that we just machined is now facing me. I'll get a dial indicator on there, and we'll tap this in nice and parallel to the fixed jaw on the vise. The technique I use for tapping this in is the same as I use for tapping in a vise, which is to say I run it under rapid feed and tap it until the needle stops moving. If you want to see more about this technique and why it works, I did a video called Tapping In that covers this and all other related indicating skills here on the mill. Now I can mill the second edge both clean and straight and also down to dimension. We're starting to need some metrology here, but this being primarily an imperial shop, I don't actually have much for metric measuring tools. However, I do have some digital stuff like this Shar's digital caliper, so it of course can be switched into metric, which is very handy for moments like this. Looking for 150 millimeters, and yeah, I think that will do nicely. The secret to precision is to wiggle it until you see the number you like, and stop right there. Perfect. Okay, good. Then the other two edges need to be parallel to each other, but of course square to the ones that we just did. So the piece is rotated 90 degrees, and I'm indicating in on one of those machined edges that we just did. And once this is zeroed out on the y-axis of the mill, then any cuts we do on the back edge will be square to this cut. Same technique, except I'm feeding manually this time for the tapping in. Once all four edges are machined, now we need a couple of holes in this thing. The drawing calls for some M6 threaded holes that hold the brackets for the feet. And conveniently, they are 28 millimeters from this edge, which puts them right in that little gap that I have in this setup. So that's handy. Next, I need to do some edge finding to get my bearings on this plate. Now, I said we're going metric for this project, but we might as well go really metric. This is a German Heimer edge and surface detecting probe. This was actually a gift from a viewer quite a while back, I'm embarrassed to say, and this is my first time busting it out and giving it a try. It's perfect for this situation, as you'll see. The very first time you use it, it requires some setup. First thing you have to do is get the probe tip to be concentric with your spindle. So you can see I've got a tenths indicator on it. That's my highest resolution indicator. And you dial this thing in just like a four-jaw chuck. It's got these little set screws around the top, and you use them to push the entire instrument back and forth relative to its position on the mounting shaft to eliminate as much runout as you can. So I got it within a tenth. This is the best I could get, and frankly that's probably within the tolerance on the bearings in this mill, so I doubt I could get it any better than that, but that's still very, very good. To use this device for edge finding, all you do is touch up the probe on the edge of your work and feed it in until it reads 0 on both of those needles. And when it reads 0, your spindle is exactly on that edge. The nice thing about this Heimer is that you don't have to do a second zeroing and moving over for the radius of the edge finder like you do with a normal mechanical wobbler style edge finder. It's just a single move, and the DRO only has to be reset once. What's nice about that is because I'm working in metric, I've got my DRO set in metric, but my edge finders are all imperial. So I don't have to switch back and forth to do those translation moves to cancel out the radius of the edge finder. So this thing is actually quite a bit quicker in most situations for edge finding, and frankly a lot more accurate than the wobbler style. What's neat is the indicator always moves the same direction no matter which direction you touch the probe, and the probe's three-dimensional. It works for touching off on top surfaces as well. You can also measure distances and do all kinds of other neat things with this device. It's quite a little machine. I centered up on X, but for Y I touched off on the rear edge, but I didn't have enough Y-axis travel on this mill to get to the other edge so that I could center up on Y. So I'm going to have to settle for just using one edge for Y and the center for X. And that's a little bit tricky. You got to be careful about using mixed references like that. More on that in a minute. Now I can center drill, and tap this pair of M6 holes that go in this end of the table. Next, I'm going to chamfer from this same setup using my zero flute chamfering tool. Normally I chamfer holes by hand because I just find it quicker, but in this case this is a work table for a bunch of fixtures that are going to be sliding across this table to hold the various tools for sharpening. So a proper chamfer done with a chamfering tool in the mill will ensure a really nice, smooth surface with no snags or anything for stuff to slide around on here. Deburring holes by hand doesn't do quite as nice a job as the chamfering tool does. I'm going to throw an end stop down here now because I'm going to flip this piece over and I'm going to chamfer the back sides of the holes the same way. This hole pattern is symmetrical in both X and Y, which is super handy because it means I can use an end stop in combination with the fixed jaw on the vise as my Y reference, and I can flip this table in any dimension, and I don't have to re-indicate anything, I don't have to re-edge find anything. I know that my hole pattern is going to land in exactly the same place when I flip it now on the Y-axis to do the other pair of holes. There's an interaction here between the size of the table and the references that I chose that's worth talking about because it can be important. Remember that I chose a center reference for X but an edge reference for Y. It was kind of out of necessity, but you got to be careful with that because that affects how any errors that you have in the dimension of your table are going to propagate into the features on the interior of that part. I like to use center references on things whenever possible because then if the dimensions of the part are a little too small or a little too large, all of the features in the middle of that part are still going to be correctly centered on the part and are still going to be, of course, relative to each other, the correct distances. Another commonly taught technique is to always use one corner of the part as your reference for X and Y, which means any error in dimension will all get pushed to one side of the part. The pattern of features in the middle will all be relative to each other, but might be shifted a little bit on the part if your outer dimension of the part aren't exactly perfect. Now, because I used one edge for my Y reference, that Y flip maneuver I did has some risk to it. If the Y dimension of my part isn't perfect, then I'm actually going to be expanding or compressing the hole pattern in the center of the part slightly by whatever error I have in the outer dimension of my plate. However, you saw earlier, I nailed the dimension on that plate, so I'm not worried about it. And those other two holes were then drilled and tapped the same way. Now, the drawing calls for the corners of the plate to be rounded with a 6mm radius, so I've got a piece of tool steel here, and I'm going to make a couple of filing buttons. I've got just enough stick out for a comfortable width around the file. I'm going to turn this material down to 12mm diameter so that I'll have a 6mm radius for reference. Start by facing off the end, as is tradition. Then I'll center drill that so that I can get some tail support in here. This is not very much stick out, but this is tool steel, which is very hard cutting stuff, so we're going to want tail support. Now I can slide the tailstock in there, as you can clearly see. That's sitting in there perfectly, very clear as you can see there. Very nice, perfect footage here, no notes. And away we go. Tool steel can be a little bit challenging to turn on small lathes. It's not as difficult as a lot of stainlesses are, but it still is a lot more difficult than mild steel. Most notably, tool steel does not like to break a chip. It's very tough. So chips don't tend to break, and you tend to get rat's nest chips like this. Now, of course, the tool that I'm using doesn't have a chip breaker profile in it, which is obviously not helping, but I found even using carbide inserts with chip breakers in them still doesn't help very much with tool steel. So I like this tool anyway. If it's not going to break a chip anyway, I'm going to use it. I'm taking fairly light cuts because I'm getting good performance out of it, and I'm getting really nice finishes, so if it ain't broke, don't fix it. I had to take a lot of passes, but honestly, if I'm not in a hurry and the feeds and speeds that I've got are working, I just roll with it. As I said, I don't have a lot of metric measuring tools. For a micrometer, I've got this digital guy. This was donated to the channel many years ago, and I haven't really used it much. It's a little worse for wear, but it does still function. So I will use this as my metric micrometer. It should be within striking distance of my dimension now. Yeah, just under 1 millimeter to go. Looking good. Of course, having DROs on both machines really helps at times like this because I can switch both DROs to metric, and that handles most of the measuring that I need to do. I don't have to go out and buy a full set of metric metrology equipment just yet. But I'll be working on that. I've got more metric projects in the queue coming up, so stay tuned. That should be my final cut now. Let's see how we're doing. Not bad. 26 microns, that's pretty darn good. I think we can live with that. Having a 3-digit metric mic is both interesting and a little demoralizing. The amount of error shown there would be within the thickness of the lines on my traditional mechanical mics. So, if you want to feel bad about yourself, get fancier measuring equipment. The surface finish on that's not quite as good as I would have liked, so I'll get in there with a little bit of emery paper and clean that up. One of the nice things about tool steel is how nicely it sands and polishes. With very little effort, it comes out really, really nice. So nice. Just like you can't stop touching it nice. Just really... Okay, settle down. Jeez. Wait, what you doing there, Quinn? Is that a parting blade and 12 millimeters of tool steel? Now, I'm always the first person to say, don't be a hero with your parting blade. If you're not comfortable parting something off, I will never judge you for taking it over to the bandsaw. There is no shame in that. However, I've got a really rigid setup here, and I decided I can do this. Let's do this. I got the parting blade honed razor sharp. I got it choked up nice and close, and I'm running slow, got lots of fluid, and we can do it. I've parted off stuff tougher than this, but these days I'm more and more inclined to part things off with the bandsaw, honestly, because it's just not usually worth the drama. But occasionally it's good to remind myself that I still can do it, if and when it's helpful and useful. And Yahtzee. Of course, in my zeal to part that off, I neglected to remember that I actually needed 2 pieces out of that, so I in fact had to cut it in half again over on the bandsaw anyway, and now I'll set them up and face off the ends. I've just got it in the 3-jaw with some aluminum shim there to protect the surface finish from the jaws. I don't have a 12 millimeter collet in which to hold these, so this is going to have to do. It's not going to be very concentric, but it doesn't matter because all we're doing is a facing cut, so concentricity doesn't matter. There are my 2 little filing buttons. On dimension, nice surface finishes. Now they just need to be heat treated so we can use them. Over to the hearth and under the torch it goes. I heat these up to kind of a bright red, dull orange, glowing kind of color. And I hold it there for several seconds to make sure that that heat is soaked all the way through. Then I grab them with some pliers that I don't care very much about and dunk them in the oil. Wiggle it around in that quenching oil. Oil that I'm using in this case is vegetable oil, which works just fine. I don't bother tempering filing buttons. The way that they're used, there's no real forces on them, so the brittleness of them being this hard doesn't actually matter. And having them be harder than the file is actually helpful in the feel of filing while you're using them. Out of curiosity, let's see if the dimension changed from the heat treating. Sometimes it does. Usually it does, in fact. They got about 3 microns, 4 microns smaller, something like that. So, yep, that's why you have to grind things after you heat treat them if they need to be an exact dimension and to be very, very hard. Before I get to the filing, I'm going to set them up on the edges of the table, and I'm going to use the buttons as templates to describe the radius that we're going to end up with. This will allow me to do some rough shaping before we actually get to the filing. It'll save me some time. So I can go over to the belt sander and knock those corners off, which I did. Now I can set up the filing buttons for the finish filing. Normally when you use filing buttons, you have a hole through at the center of the radius that you're creating. It's actually pretty uncommon that you don't. So in this case I don't, which makes clamping the filing buttons in place a little tricky. I clamp them lightly and then I use a 1-2-3 block to align the tangent surfaces with the plate on both sides. I just kind of nudge them around until I get to a point where there's no light showing between the block and the buttons on either side of the plate that we're creating. And if I do that right in principle, then the tangents are perfectly aligned with the curves on both sides of the corner. Then I snug down that clamp and I should be good to go. You could conceivably create some sort of a big U-shaped frame with pins in it that would hold the filing buttons in perfect alignment to each other, but honestly, these are just aesthetic details, so this is fine. Away I go then, starting with the coarse file, always dropping my handle on each stroke to create a nice curved profile. And you can feel when you're done because the file will very suddenly start feeling like you're just pushing it across ice. It suddenly starts slipping super easily with no resistance, and that means it's touching the filing buttons. When I'm close to that, then I switch to the smooth file and finish it up for a nicer surface finish. I got to work a little bit from the other side as well because the toolmaker's clamp keeps me from getting a perfect 90-degree tangent angle on the other side. Once I can feel that the file is no longer cutting anywhere around that profile, then you know you're done. Filing buttons are really very satisfying to use, and they're pretty foolproof. And I can pull those off of there, and you can see what a nice job filing buttons do. If you have any discontinuity where the tangent of the curve meets the edges on either side of the corner, that's going to be down to small errors in the distance of the center of your filing buttons from each side of the corner. It's difficult to get that perfect, but that's frankly true of all corner rounding methods, including rotary table setups or other more elaborate things. There's all 4 corners of my table nicely rounded with a pretty close to perfect 6mm radius. On now to some aluminum spacers that go between the legs of the table. I'm getting the copper jaws on the vise because the aluminum bar stock that's supplied in the kit is already the nominal dimension of the final parts of these spacers, so I'm treating the factory outside surfaces of this round bar as a finished surface. So I'm also using the 4 jaw because I need the hole that's going to go in the center of this to be concentric with that outer surface. Thus I'm dialing it in just as if that was a machined surface on the outside of that round bar. The good news is factory stock these days is really very good, and you can, generally speaking, treat a factory surface as though it was finished for the most part, especially on aluminum. With that dialed in, now I can face off the end, as is tradition. The stock is a little bit over length, so I'm going to face off one end, and then I'll put a nice chamfer on that with a file so we can get accurate measurements. And now I'll take it out of the chuck and flip it around, and we're going to face off the other end. And then and only then, once both ends have been faced once, can we then start measuring. That's how you get an accurate length on a part like this in the lathe. You'll note that I did not dial it in that time because it doesn't matter for this time. We're just facing off the end. What I did is, with the chuck stopped, I loosened 2 of the jaws and then retightened those same 2 jaws. And if you're careful about that, you can get it within a couple thousandths after reinstalling it without dialing it in a second time. So I measure how long we are now, then I put it back in. Now I do dial it in again because in addition to facing off the excess length, we're going to now be doing the hole down the center, which does have to be as perfect as we can get it. So for that, I do want to dial it back in. But if you noticed on the indicator at the start, we were only about 3 thousandths out after unclamping and reclamping, just by being careful which jaws we loosen and then tighten again. Then center drill and drill 6mm all the way down the center. These parts are 60mm long, so this is a 10:1 aspect ratio hole, which is very, very deep. That means we got to do a lot of chip clearing. Drill flutes have a chip clearing efficiency that is much lower than a 10:1 aspect ratio. So a quick way to do that, because this is a through hole, is to simply unlock the tailstock, pull it back, clear the chips, push it back in until the drill touches up again, lock the tailstock, wind a little bit more, rinse and repeat. The disadvantage to this approach is that you lose the position of the tailstock each time, but for a through hole that doesn't matter. Or if it's a blind hole that doesn't have to be very accurately depthed, that's also fine. Finally, the drawings call for a generous chamfer on these holes to make sure that the mating parts seat tightly against these surfaces. So I'll do that with my zero flute chamfering tool. I flip the part over to do the other end, and again I didn't bother dialing it in because for a chamfer, a couple of thousandths of runout isn't going to hurt anything. And the outside of the part is still that factory surface, which doesn't look very nice, so I took it over to the Scotch-Brite wheel and shined it up a little bit. There's the final spacer for the legs. We actually need 2 of those identical, so I made 2. Let's see how we did on the length, just out of curiosity. Yeah, all right. 10 microns. I think we can live with that. Next up are these L brackets. There's 4 of them in the kit, and these are an example of these semi-finished parts that the kit has a lot of. These have already been laser cut and bent, and 2 of the holes are finished. However, the 3rd hole is just a pilot hole that was made by the laser cutter. So it's our job to finish this out to dimension. I line it up on the spindle with a gauge pin the same size as that pilot hole, and then drill it out. There's 4 of these, and we actually need 2 different hole sizes. 2 of the holes are slightly larger than the other 2. It's an important detail in the drawing that would be easy to miss. Then the table legs are these slotted dealios that allow you to adjust the height and angle. They are similar, they get drilled out. And we've got enough parts to do some assembly now. Let's see how things are coming together. As with any project like this, it's going to come together and come apart again 600,000 or 700,000 times during the project, but that's completely normal. So you can see that the L bracket's attached to the underside of the table, and then the legs go in between the spacers like so. And then these really long bolts are included in the kit. The kit includes all the hardware. If you get the middle option, like I said, not the drawings and not the finished one. Well, I guess the finished one comes with the hardware too, otherwise it wouldn't be very finished. On the ends of these bolts, there's these little discs that have a face groove in them for holding an O-ring, and this provides the friction element for the adjustment handles. It's kind of a neat way to do this. I haven't seen it done this way before. We'll see how it works. This would be in lieu of something like locking teeth or something like that, like you might see on a bench grinder rest. So that washer goes on there, and then a standard kip handle goes on the other side. So when the kip handle is all the way tight, the O-ring is fully compressed, it's metal on metal, and that's going to lock everything tight. However, when you loosen that kip handle a little bit, that O-ring is going to provide some friction and allow you to make nice adjustments without the whole thing getting floppy on you. Then there's an identical assembly at the bottom with these longer brackets that form the actual feet of the table. And these provide some height adjustment and also give you some shiftability in the forward and back, I guess, to align the table with your bench grinder as needed. Let's give this thing a little test drive, see how it works. Those kip handles seem to work nicely. The O-rings seem to do what they're supposed to. They are a little bit fussy. You got to get that initial bolt tightness just right, because the kip handles do have a slight tendency to cause the bolt at the other end to turn. But if you get the initial adjustment right, then it does work. I may want to do some kind of a locking thing on the bolt heads just to make sure. Like you could put a little tack weld on there, or maybe a little bit of a punch mark on there to hold them in place, something like that. We'll see. But there isn't a lot of force on this table. You're just resting some sort of a sliding fixture on it, and grinding wheels don't create a lot of tool pressure, so I think for the amount of force that's going to be on this, it should be adequate. It certainly seems sturdy. When everything's locked up, it's very sturdy. It certainly looks like a table anyway, and I love those rounded corners on there. That was definitely worth doing. Safe and pretty. Well, that's all the time we have for this week. We will get more done on this tool sharpening system very, very soon, so keep watching. Thank you very much for watching, and thanks to my patrons for making all of this content possible, and I will see you next time.